I feel stupid, and I'm not sure whether this is the right thing to do or not. I said that today I was going to give you guys a video with a review of First Lensman, but I went and I checked the science news again, and there's actually something really cool going on that was just published in Nature that I think might be worth talking about because, like, I don't know. I really enjoy all the like astronomy news and stuff like that, and all the neat, weird stuff that happens in like the world of like looking at things far, far away and trying your best to figure out what the hell they are. You know what I mean? So I don't know. I think the Lensman review is going to wait one more day because we are going to talk about a we're going to talk about a little known type of star, not star actually. I mean, technically it's just a gigantic planet, right? Called the brown dwarf. And apparently the first brown dwarf that we found like 30 years ago has been the subject of some weird controversy over the last few years. And it's kind of neat to see how our understanding of these things kind of improves step by step, and I'll show a little bit of that. So, yeah, let's switch over to the internet and we'll take a look at some stuff for actual science. All right, welcome to the science. This is an article that was published by the Associated Press. A brown dwarf discovered 30 years ago is actually twins circling each other. It's talking about the object known as Gliese 229b, which is a brown dwarf that orbits Gliese 229a, or at least it was thought to be a brown dwarf, but a recent study has basically said it looks like it probably is actually two things that are orbiting each other very closely. Now, you may not have heard of a brown dwarf before. It's a type of star. It's not actually a star. It's like I guess you could call it like a failed star. Basically, it is an object that is not quite heavy enough to maintain hydrogen fusion at its core. Average normal stars maintain their heat by fusing hydrogen into heavier elements at its core. A brown dwarf is a collection of mass that is not heavy enough to get temperatures at its core high enough for the hydrogen to fuse. And therefore, it's really just kind of like a big, mostly inert ball of gas for the most part. And Gliese 229b is one of these things. It orbits a star called Gliese 229a, which I believe is a white dwarf. A white dwarf is a dead star. A white dwarf is a star that has burned through all of its hydrogen and is now, and then usually they go nova, and then they collapse into this little white ball that is held larger than zero by electron degeneracy pressure. Basically, when you squeeze matter together closely enough, you end up with something called degenerate matter from electron degeneracy. Let's make this a little bigger for you guys. So basically, the matter of a white dwarf star, we believe, is basically a collection of positively charged ions, largely helium and carbon nuclei, that are floating in a sea of electrons. And the electrons are forced into the electronic states that they're in because of the force holding them all together. So degenerate gases are weird stuff. We're not going to get into that, but that's what a white dwarf is. A brown dwarf is just mostly hydrogen. It's not big enough to sustain nuclear fusion of hydrogen, but it might fuse a little bit of deuterium and a little bit of lithium. Those are also pretty easy to fuse, and they go at lower. They end up self-sustaining at lower temperatures than hydrogen does. But of course, the problem with deuterium is that it's like 1/4000th of actual hydrogen, and so even if you can fuse deuterium, you can only fuse a very, very small fraction of what's actually in the star itself. So realistically, what a brown dwarf star might be is it might be a warm ball of hydrogen gas that has like a little metallic core, and so this particular Gliese 229b is one of those brown dwarf stars. But what I found is that back in 2019, there's a paper where they estimated the dynamical mass of Gliese 229b as like 70 Jupiter masses. So this is a big freaking thing. It's not quite big enough to be a star, but it's really, really close. And so this is a secret that maybe you will find helpful and handy. I don't know. But like arxiv.org is a preprint archive. A lot of people don't know about this who aren't actually like physicists or scientists. But basically, it used to be LANL, but now it's Cornell, and they basically have this archive which is a preprint place. And what responsible scientists do is they will put an earlier version of their paper up here on archive before it gets published in a journal. So this particular paper ended up published at, let's scroll this baby back up, but it ended up published at the Astronomical Journal. But like you can get, and the Astronomical Journal is actually an open journal, so you can like just look at it here. But for a lot of journals that are not open journals, if you look up the names and like a couple of words out of the title, you might be able to find a preprint on archive that gives you an almost done version of the paper. What you want to look for is you want to look for this paper actually being published somewhere, because that shows that it has gone through peer review and been accepted through that process. So, this is a way to get scientific papers without going to your university. And scientists use this all the freaking time. So, what does this paper talk about? Well, this paper is basically a mass measurement of this Gliese 229b T-dwarf. And these brown dwarves can have masses up to 80 times the mass of Jupiter, depending on metallicity. So metallicity is how much metal there is in the thing. And that can, depending on how much of that there is, it might make it harder for there to be hydrogen at the center. Imagine, for instance, that you have like an iron core, and the iron's not going to fuse for sure. But imagine that you have a fairly large iron core. Well, the hydrogen that might fuse now has to be at the outside of that iron core, which makes it less likely for the hydrogen to fuse. It needs the mass of the whole thing would need to be higher for hydrogen fusion to occur. Therefore, more metallic brown dwarfs can be heavier than low metallicity brown dwarfs. These systems have very long orbital periods, 10 to 30 years, which means that you have to basically patiently monitor their orbits for a very long period of time in order to get any useful scientific data. Now, we've found a bunch of these T-dwarfs, or T-dwarves, and most of them have fairly low masses, between 30 and 50 times the mass of Jupiter, given their low temperatures. But there have been some of these T-dwarf masses that are very, very high, to the point where it's like, well, why aren't these things fusing hydrogen? They probably should be. In addition, when the objects become so massive, they actually cool more slowly because it's harder for radiation to get from the center to the surface. Basically, eventually, it takes that radiation, thousands of years to make that move. And therefore, these objects can't actually cool down, so they maintain a very high temperature. And if they stay hot enough, they can't actually form any methane, which means that you wouldn't see any methane in their spectrum. So this 229b, this paper is all about their work in trying to figure out, from an orbital modeling perspective, how heavy 229b is. And they come to a conclusion that we'll get to down here. They do a bunch of simulations, and they do a bunch of fits, and the answer that they arrive at is that the size of 229b is about 70 times the mass of Jupiter, whereas the host star is that white dwarf, which is about half as big as the sun, and it's about, what did they say, 12 light years away or something like that, 18 light years away. So you have this very slow moving system. You have this very weird heavy brown dwarf, and they kind of in this paper they kind of mention like, hey, we considered the possibility. You're gonna like this actually. We considered the possibility of it being a multiple object, like a binary brown dwarf or something like that, and we don't think so because our pictures don't show any evidence of it being binary. But look at how low resolution these are. Then they say that GI 229 or GL 229b's absolute magnitude is normal relative to other objects of comparable spectral type and color. The mean T7 dwarf has mass of 15 has magnitude equal to 15.54 plus or minus 0.25 compared to Gliese 229b, which is 15.21. But here's a trick that scientists will often do. The error is the RMS of 4 objects. So they basically have 4 objects that they're like, well, these T7 dwarves look like this other thing that we also call a T7 dwarf because they're stupid heavy and yet pretty dim for their weight. But like the amount of statistical data that they have here is very small, and so realistically, they're not actually making that much of a conclusion about Gliese 229b being binary or not. They just don't have the resolution to determine such. But yeah, that's what this Nature paper is about. Basically, these guys have done some additional interferometry. They've used the gravity interferometer and the Cry-Res Plus spectrograph at the VLT. And what they say is that they can independently resolve 229b into 2 components, BA and BB, which settles the conflict between theory and observations in 2 ways. Number 1, it says, hey, you guys didn't have the resolution to see this back in 2019, and that's fine, but, you know, new data has come in. And it also says that this is why this particular T7 dwarf is so dim for its apparent weight, because it's actually 2 smaller brown dwarves that are in a tight orbit of each other, where they are closer range. Where does it say this? It does not. Or it says it's separated by 16 times the Earth-Moon distance. So it's 16 times, these two brown dwarves are 16 times further away from each other than the Earth is from the Moon. So the Earth and the Moon distance is like 300,000 kilometers. So 3 times 16, 48. So this is about 4.8 million kilometers apart, which is pretty close considering that they're, light years away and we're still able to differentiate them from each other. But yeah, this seems to explain why they are so dim compared to what they should be considering their weight and age. So yeah, this is kind of a neat little discovery, and it's kind of nice that we can actually trace it back all the way back to October 2019 when the first version of this paper came out, and they said, hey, this thing weighs like 70 Jupiter masses, and it's really dim for that, weight, and we're not quite sure why. And this gives us our answer. It's actually 2 different objects with masses of 38 and 34 masses of Jupiter. And they're separated by, 5 million kilometers approximately. So that was pretty cool. I thought that was pretty neat. At the same time that I was looking through articles for this, I found this, which is kind of cool. I saw like a YouTube recommendation the other day that was like, hey, if you go outside right now, you might be able to see an aurora all throughout the U.S., except in Hawaii. Poor Hawaii. But like, I saw it like an hour after it posted, and it was already too late by then. But apparently there was a solar storm a few nights ago that made it so that even as far south as like, Arizona, you could see auroras. And, I found this article where they said, hey, there might be... Here we are. We still could possibly get some good shows in the next few months, she said. So basically, there's the possibility that we might that if you're even if you're in the United States, even in the southern United States, you might be able to see an aurora, which is something I've never actually seen in person. So what I did is I went and found this. Now this is cool because this is the Space Weather Prediction Center alerts, watches, and warnings, and this will tell you. I'll put the link in the description. But if you check this every evening or something like that, you might be able to find a notification that, hey, there's a big solar storm happening, at this time, and it'll tell you it'll tell you where you might be able to see an aurora. If we scroll down, solar flare, Canada and Alaska. Here we are. Aurora may be visible at high latitudes, northern tier of the U.S., such as northern Michigan and Maine. That was the 13th. Northern Michigan and Maine. Aurora may be seen as low as Pennsylvania to Iowa to Oregon. Low as New York to Wisconsin to Washington. High latitudes. Washington State. So if you go on this website and you check this website every evening before it gets dark, you might actually see, hey, we're expecting this kind of thing to happen. And if you see like the Pennsylvania to Iowa to Oregon thing, you might be able to see an aurora yourself if you're somewhere in the United States. So yeah, this is a cool website. I found it for you guys. I'll put the link in the description. And that's all I've got as far as real science to talk today. So yeah, hopefully you guys found this entertaining and maybe a little bit informative. I didn't know that much about brown dwarfs until today, so I had to look it up and kind of poke around a bit to figure out what it was. And the thing where they were talking about metallicity was kind of interesting. Like, what the heck is going on with metallicity? I had to figure that one out too. But anyway, that's all I've got. So let's get back to our regularly scheduled, video. So yeah, some neat stuff in the night sky. That double brown dwarf thing is kind of neat because it suggests that the other really heavy brown dwarfs that we've seen might also be binaries that we just can't tell them apart at this point. There's also a quick little thing about what the AP person says, like, this is so weird, and it's like, from a physics perspective, it's not really that weird, because, forgive me for saying this, but it's going to be a really bad joke, but angular momentum conservation is a hell of a drug. So yeah, that's all I've got for you guys for today. Brown dwarfs are cool, night sky is cool, auroras are cool. Check the description for links to all the different pages, especially that NOAA alerts page, because if you want the opportunity to see an aurora in the next couple of months, this might be the best time to do that for the next 11 or so years, because the sun cycle is about 11 years, and if you're going to see an aurora anywhere south of Alaska, your best chance of doing so is probably probably your best chance was Monday, because that's when they actually saw it. But the best chance to see another one, which is possible, although not super likely, is going to be in the next few months. So, yeah, you can kind of tell that first Lensman did not blow me away in any significant way, just based on the fact that I've managed to put off doing a review of it for 2 days. But I don't know. So when there's something cool actually happening in the world of real science, it seems like science fiction kind of takes a back burner when something actually cool just happened. And to me, like, a new advance in, like, ooh, we can tell brown dwarves apart, when they're only 5,000 kilometers apart, or 5 million kilometers apart. And it's like, that's actually kind of neat. More advances in observing the world around us means that we can hopefully better understand it. So yeah, that's all I've got for today. Tomorrow, first Lensman review, and I'll try not to put it off again, because I do want to get that out there, because it was good, just not like mind-blowingly good. But if you like pulps, you'll probably love it. So yeah, brown dwarves, auroras in the southern United States, and yeah, fun stuff. Have a good day, and I'll see you next time.